Okay, welcome one more time to Introduction to Structures. This is lesson 10, Axial Direct Stresses. So today we are going to study in more detail the axial stresses. But as an introduction, let's remember that we have basically two types of stresses in the analysis of structures. We have the direct stresses, which are stresses which are normal to the cross sections. For example, the bending stress is a direct stress, and when you bend a beam, a simple supported beam, for example, as in this example, you will produce compression on top of the neutral axis and the neutral plane, you can see here, and you will produce tension under this axis. And the distribution of these stresses will be linear, as you know from previous lessons. So this is a direct stress because the stress is normal to this cross section, which is vertical. In the case of the axial compression, for example, where you have a piece of a structure subjected to compression in both sides, you will produce an internal stress of compression, which is negative by convention and will be uniform across the cross section. The same thing happened with the axial tension, where you have this piece of structure under tension, and you will produce internally a distribution of a constant tensile stresses, and these stresses will be positive by convention. And the important thing is that the distribution is uniform. In order to have compression or tension, and pure compression and tension, let's say, you have to apply these forces in the same line, of the same direction of this neutral plane or this axis, the barycentric axis of the cross section of this structure. Because if not, you will produce moments, and this moment will produce bending. And in this particular example, this is pure compression, this is pure tension, and this is bending. So bending, axial compression or axial tension, just because they are all stresses perpendicular to the cross section, which is in any case is vertical, then they are called direct stresses. There are shear stresses as well, and for example, in here we have a structure that is subjected to these two forces that tend to displace, to move this cross section one regarding the other in the vertical direction, producing a distribution of stresses but in the plane of the cross section. So these stresses are not perpendicular to the cross section, they are on the same plane of the cross section. The distribution of this shear stress is usually parabolic, and especially in rectangular cross sections. Let's say for this first example, this is a rectangular cross section. So the distribution of the shear stresses is parabolic. So as a resume, the bending stresses have a linear distribution, compression and tension have constant distribution, and shear stresses have parabolic distribution. In the case of the direct axial stress, which is the topic to study in this video, remember that the forces have to be applied exactly on the barycenter of the cross section, because if not, we are going to produce moments. So if we have this condition, if we accomplish this condition and we have the forces in line with the barycenters of every cross section of the structure, we can have tension, and this is positive. When you pull the structure, like you can see in the screen, or when you compress and you shorten the structure, you will produce a stress which is called compression is negative. Of course, it's not necessary to apply these forces in the horizontal direction exclusively. For example, in any inclined direction, you can have tension, and this is the case of pieces of a structure that we usually call tensors. Tensors are subjected to tension, and this, remember, this is positive. And in columns, for example, even in engineering, there are many columns that are subjected to compression, and this is the case, and this figure represents a column that is subjected to a compression because this force P applies in the barycenter G of the structure, of the cross section. The definition of the stresses, the constant stresses we are going to have in tension and in compression, is very simple, and we call FA because A is axial. So F is a stress. The axial stress is equal to the force applied to the structure at the very center of the cross-section divided by the area. So the units for stresses are obviously forces divided by areas. In this case, for example, as an example, we have newtons as a force divided by square millimeters as an area. When we apply an axial force on a structure, let's say, for example, we have this beam in here, which is fixed to the left side of the beam and is free to the right side, and we apply a force to the right side, to the right extreme, we're going to deform this structure, and we're going to produce this reaction in red in here with the opposite direction to keep this structure in equilibrium. And you are going to increase the length of the beam, yes, because you are going to deform the structure, and you're going to reduce the dimension perpendicular to the length of this beam. But if we focus the study for the moment in the elongation, we have an initial length called LO, and delta L is the increment of the length because the force applied on the right extreme of this beam. There is a quantity called the strain, the direct axial strain of this beam subjected to axial forces, that is defined as the relation between the increment delta L of the length divided by the original length L. Because these two quantities are lengths expressed in millimeters or meters or kilometers, they cancel one to each other, and the strain E is adimensional. So the direct strain is non-dimensional or adimensional, and usually is very, very small. It's a value that is in the order of 10 to the minus 6 meters or something like this. So there is another thing we need to understand when we start studying deformation and we start studying stresses and axial stresses in particular. In order to see the relation between the stresses and the deformation, we need to study the relationship between the stresses F and the strains, which represent the deformation by unit of length. And the relationship is made through this coefficient or this property called Young modulus, and the Young modulus is the stiffness of this material, is the capacity to take loads without being deformed, and it expresses this E, this Young modulus is expressed in units of stresses. Because F is a stress, E has to be a stress because remember E is adimensional. So in order to be consistent in this equation, we need the same unit for F and for E. And E, the Young modulus is the most important property of the materials we are going to study in civil engineering. So the Young modulus is the stiffness under deformation, against deformation of any material. So as you see, the relationship between the strains and the stresses is linear because E, the Young modulus, is usually a constant value, and then this equation is a linear equation. So the variation of the stresses regarding the strain will be linear, just multiplied by a constant, which is the Young modulus. And again, the units for the Young modulus are unit of stresses. So what we have in here is another concept, very important concept called Poisson effect. I mentioned a minute ago that when you deform this beam, because this force is P, you will produce a contraction in the perpendicular direction. You will produce an increment in the length because the force, but automatically, because the Poisson effect is called, there will be a contraction in the perpendicular distance, the perpendicular distances to the length of this beam. This contraction will be expressed by a coefficient called Poisson ratio. The Poisson ratio nu is equal to minus the strain in the perpendicular direction to the beam divided by the strain in the direction of the length of the beam. And the values of this Poisson coefficient, it varies between 0.3 and 0.5 for usual materials we are going to use in civil engineering. Of course, there is more variations, and there are materials with less than 0.3 Poisson ratio, but 0.5 is mathematically the upper limit of this coefficient. In order to understand a little bit more about this concept, we're going to do an exercise now. So let's say we have a column under a center load applied in the very center of these cross sections for this column, and the cross section of this column is a particular one, is an annular cross section. It is to say the cross section is only the black region in here. So this white region, the circle, is hollow, and the internal diameter of this cross section is 300 millimeters, so the radius is 150, and the external diameter is 350 millimeters, so the external radius is 175 millimeters. The Young modulus for this exercise is going to be 200 kilonewtons per square millimeter, or 200,000 newtons per square millimeter, and the load applied to the column is 2,000 kilonewtons. The length, the total length of the column, is 5 meters. And we expect to have a deformation delta L that will shorten this column because the application of this force P in here. After the application of the force, we are going to have a reduction of this length, 5 meters, and we are going to have a Poisson effect, producing an opposite deformation in the perpendicular direction. It is to say, we are going to expand the diameter of this column a little bit because of the Poisson effect. So the cross-section area for this annular cross-section will be pi square radius, the square external radius, minus pi multiplied by the square of the internal radius, and this will be equal to 25,525 millimeters square. So with this calculation, we have the area of the black area in here of this cross section. The axial stress, which is the force divided by area, will be negative because it's compression by definition. So this will be equal to minus 2 million newtons, because we are transforming these 2,000 kilonewtons to newtons, divided the 25,525 millimeters squares. All of this is equal to minus 78.4 newton per square millimeter. It is important to preserve the sign to express that this stress is compression. The axial strain for this column will be the axial stress divided by the Young modulus. The axial stress is negative 78.4 newton per square millimeter, we just calculated in here, and divided by the Young modulus in newton per square millimeter, which is 200,000. So the strain, the axial strain, is equal to minus 392 times 10 to the minus 6, which is adimensional. Now, if we want to calculate the shortening of this column, it is to say the delta L will be equal to the strain multiplied by the original length. Remember that the definition of E is delta L divided by L0. So if we do this operation, this is negative, as we calculated in here, because it's compression, multiplied by the original length, we have that the shortening is equal to minus 1.96 millimeters for this particular exercise. You will be wondering for sure what's happened with all the concepts we have studied for beams, and all of them apply to this exercise as well. This is the reason that why I'm putting in here the reaction. If we do the summation of forces in the vertical direction, evidently the reaction for this column that is fixed at the bottom will be R equal to 2,000 kilonewtons, because the summation of forces in the vertical direction. Because the forces are applied to the barycenter of every cross section, there is no any moment, and there is no any horizontal reactions or actions for this problem. So this is the only reaction we are going to have in this exercise. And because this piece of structure is subjected to compression, and constant compression of 2,000 kilonewtons, we can sketch in here the axial force diagram that represents the internal forces of this column for these external loads. Of course, we are not taking into consideration here the self-weight of the column. We are going to do that in future exercises. So this is all. Thank you very much.